We're going to look at a Peleton example in simple linear regression. Peleton uses the RPMs, or rotations per minute of the wheels, to predict the output totals for riders, and then it reports the average readouts for riders. Use the following output to figure out how to analyze a simple linear regression problem. Typically, we start with a scatter plot and we ask ourselves, what is the dependent variable that I want to predict? That's going to be output on the y-axis. What is the independent variable? That will be RPMs located on the x-axis. So when I go to interpret this scatter plot, I note that it has a positive slope and the points are fairly close to that regression line, the red line in the middle. There is a curve that's present that we'll learn to account for in Chapter 4. So what I'm looking at, this regression line minimizes the squared distances between the points and the line. Therefore, it is the best fitting line. Then I can look at the correlation matrix. Again, we ignore output with output and its correlation of 1, and instead we want the correlation between output and RPM. That value is 0.957. That would tell us we have a strong positive predictor. It's strong because 0.957 is very close to the absolute value of 1. That's the degree of the relationship. The nature is positive. Next, we go and find the actual least squares equation, or line of best fit. Look under linear fit. It says output equals negative 231.79 plus 6.112 times the RPMs. So we can insert different values for RPMs into the equation and predict output. If we look at the R squared value underneath, under summary of fit, it is known as the coefficient of determination. We take 0.9159, say, and multiply it by 100 to make it a percentage. Then we interpret it as 91.59% of the variation in output on a Peleton is explained by RPMs. Then we can look and see how many samples were in the study. That's under observations. And there were 41 riders and bikes in the study. If we want to interpret the standard error of the slope, look for the value called the root mean square error. We would say approximately 95% of the predicted outputs will be within plus and minus 2 times 26.945. Or if you work it out, that would be within plus and minus 53.89. The 2 comes from the old empirical rule, where about 95% of our values fall. Next, we're going to test and interpret the slope. If you look under parameter estimates, you will see the y-intercept, then beneath that, RPMs. 6.11 is the coefficient for RPMs, or the estimate. That is the slope. We test the slope by taking HO, beta sub 1, the symbol for the slope, setting it equal to 0. Then the alternative hypothesis is the opposite. Beta sub 1 is not equal to 0. Next, we find the T ratio for RPMs. That is your test statistic. It's 20.61 with a p-value or probability less than 0.0001. So that means that there is less than a 0.0001 chance that we would get a t-value as large as 21.61 if the slope were really 0. So we reject HO. We definitely have slope. We could also place a confidence interval on the slope. Those values range between 5.51 and 6.71. So 95% of the time, the slope could range between 5.51 and 6.71. This slide shows us all the different types of output I'll have you try to understand when we do a simple linear problem. In the very first column, you simply have your observation numbers. So our output is what was actually observed in the sample. Then next to it would be the RPMs that were associated with those outputs. Our next column, predicted output, would occur when I substitute the RPM of 65 into the equation and calculate output. I get 165.49. The residual is the difference between the observed output 149 and the predicted output of 165.49. When I look at negative 16.49, I can't really discern whether that's large or small, so I have to standardize or studentize that value in the next column. When I put it on a scale, a normal scale, those studentized values that fall between 0 up to the absolute value of 2 are completely normal. If they fall between the absolute value of 2 near the absolute value of 3, they're suspicious. Anything around the absolute value of 3 or more is a severe outlier, and those need to be excluded from the data. Then we would rerun the regression equation without those points. Next door to that, I have a confidence interval with a lower and upper value for the mean output. We'll discuss how to interpret this in a minute. The individual confidence interval would be for a single Peloton rider. So we always want to do residual analysis before jumping into our predictions. A given assumption is that the mean of the residuals is 0. That's just always true based on the nature of regression. The second one we'll check for, just as we did previously. There should be no severe outliers. So if all the values are under the absolute value of 3 in the studentized residual column, you're good to go. You don't have any severe outliers. Next goes hand in hand with the idea of no severe outliers. We want them to have a normal distribution. So you look at the normal plot. If all the data points fall within those red dotted lines, you're good to go. But if you have values sticking way out in left field or right field, or pull far away from the other data points, those would represent severe outliers, and it would not be normal, it would be skewed. Finally, we want the residuals to be random. I didn't talk about this in the chapter, but go ahead and learn this. In figure 3.5, random residuals look like a shotgun target. So that's good. That's what we want them to look like. But non-random residuals may have a pattern. One pattern we might see is a curve, as we see here. We'll deal with that and get a better model in chapter 4. For now, we'll just ignore it. So again, referring to table 3.1, I've cut and pasted a portion of the output. At the very bottom, there's a dot for the output. That means this is a value I'm predicting. It wasn't part of the actual sample. So what if a rider got 100 RPMs? Predicted output would be 379.41. Then I go over and I can interpret the confidence interval. That's going to be on the mean for a lot of riders getting 100 RPMs. So we would say that the mean output for those riders getting 100 RPMs falls between 367.49 and 391.34 using 95% confidence. For one single rider, look over to the individual output. This is known as a prediction interval. So for one single rider getting 100 RPMs, the predicted output will be between 323.62 and 435.21, 95% of the time. This concludes what we're going to do with our values in simple linear regression. I urge you to go over this particular output several times, look in the book at your examples, read through and try to work them on your own, then check your answers with the answers in the book.